Alright, this is the last part for the entropy videos, and all I'm going to do is work out 2 different example problems showing you how to use the delta G formulas that we've learned about so far. So in this first one, it says, using the standard free energies of formation for the reaction, blah, 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 calculate delta G naught, so delta G at standard conditions, and then delta G for a mixture with this composition. Now, you might be looking at this and going, oh, dear Lord, where do I begin? Well, they told us where to begin, using the standard free energies of formation. So I'm going to go to the back of my chemistry textbook and I'm going to look up the G values for each of these 4 compounds or elements. I suggest you pause this video and do the same. Either look it up on the internet or look it up in the back of your chemistry book. So the G values for each of these compounds. For H2S, we have a value of negative 33.01, and the units on all of these are kilojoules per mole. The value of G for oxygen is actually 0. For pure elements in their pure state, the G values are 0. For water, it is negative 300.4. And be real careful whenever you're looking up G values, or any values actually in the back of a book for water, that you have the right state. So we are dealing with gaseous water, not liquid, so make sure you've got the right G value there. And then for SO2 is, for SO2 is going to be negative 228.57. And so now to calculate the standard change in Gibbs free energy, all we have to do is sum up the products and subtract the sum of the reactants. And again, because the units on G are kilojoules per mole, we have to take into account the coefficient. So I'm going to write that down in, actually I'm going to write it up here so I can keep them separate. So delta G naught is going to be equal to the sum of the products, which in this case is going to be 2 times negative 300.4 plus 2, because they both have coefficient of 2. 2 times negative 228.57. Then I'm going to subtract the sum of the reactants. So I'm going to take 2 times negative 33.01. And I'm going to add to that 3 times a value of 0, which I know is 0. And some of you guys are probably going, well, why am I even taking the time to write that? Because if I don't, inevitably some person's going to be like, hey, you didn't factor in for your Gibbs free energy value of water. Well, yes, or of oxygen. And yes, I did. There it is. It's right there. So you plug this into your nifty little calculator, and you end up with a delta G of reaction of negative 991. Let's see, we're allowed 1 decimal place. So 991.9. And this is kilojoules for that one. Okay, so that's the delta G value of this delta G naught, the standard delta G value for this particular reaction. Well, now they want to know, well, what's the G value if these are our conditions? And I apologize for not, I can't figure out how to get that to be a subscript when the rest of it's already a subscript, so I'm sorry that that looks a little funny. So the way that you do this is you use the last formula that we got was delta G at non-standard conditions is going to be equal to the standard delta G plus RT natural log of Q. And Q looks just like the equilibrium expression for K, except instead of being at equilibrium, it's the conditions right now. So if you're going, okay, I totally forgot how to write K. Well, K, and since we're dealing with gases and all of our information was in pressure, it's going to be Kp, is going to be equal to the pressures, the partial pressures of the products over the partial pressures of the reactants. And so each product, we've got the partial pressure of water, and that is going to be squared. Here, I'll do this. Square that times the partial pressure of SO2, sulfur dioxide, also squared because of the coefficient. And then we're going to divide that by the partial pressures of the reactants. So we've got the pressure of hydrogen sulfide gas, also squared because it's raised to the second power. Or I'm sorry, it's got a coefficient of 2. And multiply that by the pressure of oxygen gas raised to the third power because it has a coefficient of 3. So if we want to calculate Q looks just like K. You calculate it the exact same way, except instead of equilibrium pressures, we're using the pressures that we are given. So starting with my pressure of water, well, that's right here, so 0.5 squared. And now I'm going to do the pressure of SO2, which is this guy, so 0.750, also squared. And then divide that by the reactant, so the pressure of hydrogen sulfide gas, which is right here, 1 atmosphere, squared, times the pressure of oxygen, 2 atmospheres, raised to the third power. And you plug all this mess into your calculator and you end up with 0.0176. And so that's my value of Q. I'm going to plug that in right there. And now I'm going to start plugging stuff in. So delta G is going to be equal to delta G naught, we figured out up here, was negative 991.9 kilojoules. Plus, remember how I said before R is in joules per mole Kelvin, and I'm just going to go ahead and use it as kilojoules per mole Kelvin. So I'm going to say that R is 0.008314 kilojoules per mole Kelvin. Multiply that by the temperature, and it says that the temperature is 25 degrees Celsius, so that's 298 Kelvin. And then we multiply it by the natural log of 0.0176 because it's the natural log of Q. So now working this out, oh sorry, this is kilojoules per mole. This is kilojoules per mole. Had a brain fart. Happens. And so my Kelvin is gone, and I'm left with this ends up being kilojoules per mole. And this whole thing all together, this works out to be a negative about like 8, negative 9, something like that. And it worked negative 10 maybe. It works out to grand total delta G for this particular reaction is negative 1002 kilojoules per mole. Yay! So I got one more example for ya. The standard free energy change for this reaction. Hey, look at that, they gave us delta G naught. So delta G naught equals negative 118.4 kilojoules per mole. For the decomposition of potassium chlorate, this is the starting reaction for the Screaming Gummy Bear. If you haven't seen a Screaming Gummy Bear video or Screaming Candy, you really should. It's very entertaining. So now the question wants us to calculate Kp for this reaction and also wants us to calculate the pressure of oxygen gas. So we're going to use the reactions that we were given. Since it wants us to calculate K, we're just going to use this guy. And this will very easily enable us to solve for K. So I'm just going to plug in the information that I have. I've got negative 118.4 equals negative, again, using the kilojoules version of R, 0.008314. Multiply that by the temperature. Temperature is 25 degrees Celsius, so we're dealing with 298 Kelvin. And then multiply that ln of K. We don't know what K is. So you rearrange all of this, and you end up with that the negatives cancel, first of all, and you end up with the natural log of K is equal to 47.8. So now how do you solve for K? Well, the natural log is E. The inverse of natural log is E raised to some power. So K is going to be equal to E raised to the 47.8 power. Kind of crazy looking. And so we figure out that K, solve this, is equal to the absolutely gigantic number of 5.68 times 10 to the 20th. So this reaction lies very far to the left. Not going to be any of this stuff left over. And that's not all the question asked for, though. The question said calculate K, so we have done that. And then also calculate the equilibrium pressure of gas. Well, to be able to do that, we have to have the equilibrium expression. So K is going to be equal to, and this is Kp as well. These are all Kp's. K is equal to, we take the partial pressures of the products and put them over the partial pressures of the reactants. But if you look at your reaction, you'll notice oxygen's the only gas here. Solids and liquids do not participate in equilibrium expressions. So Kp ends up just being equal to the pressure of oxygen gas raised to the 3/2 power. So we know that Kp is equal to 5.68 times 10 to the 20th. Well, the inverse of something raised to the 3/2 power is something raised to the 2/3 power. So we're going to do the same thing to both sides, raise this to the 2/3 power. And these guys cancel out, and so we need to take this number and raise it to the 2/3 power, which these numbers are just getting really crazy looking. And so this ends up working out to the pressure of oxygen gas is 6.9 times 10 to the 13th, and this is pressure, so it's atmospheres. This is a crazy high atmosphere, and I can't imagine having anything in my lab capable of holding a pressure that high, but it's what it calculated out to be. So that is all I have for the entropy notes. I probably will make a video working out just a few more old free response problems about entropy, so y'all can look forward to those tomorrow. See you later.